Chapter 21 is an introduction to organic chemistry. And we've only got a few more chapters left, and they're kind of like a survey of courses that you'll be taking in future years. So we'll talk about organic chemistry here, a very brief introduction to a topic that will require two whole classes worth of study, probably in your next year. And then we'll talk about inorganic chemistry, which is also its own course, and biochemistry, which is one or two courses depending on what you choose to take. So I'm going to actually try to go through these rather quickly. We're a little bit behind schedule, and I'm also just trying to simplify this course as much as I can to make this distance learning a little bit more manageable for you all. And I think that's not a terrible idea to pare these down as quick and as basic as we can, because you're going to be covering all of these topics in much greater detail in the future. But organic chemistry is the study of compounds which contain carbon. And there are a few carbon-containing compounds that are not considered organic, like, say, carbonate, which is part of minerals, or carbon dioxide. That's sometimes called inorganic carbon. Steel has carbon alloyed with iron. But for the most part, if a compound has carbon in it, then it'll be considered organic. Carbon's small atomic radius, its ability to form 4 bonds, and its ability to bond to other carbons and form long chains of carbons all make it possible for large and complex organic molecules to be formed. The simplest organic molecules are hydrocarbons, and that's what we'll start with today. And they're composed entirely of just hydrogen and carbon, hence their name, hydrocarbons. So because structure is important to organic molecules, usually a chemical formula alone is not really sufficient to carry all the information we need. So here we have table 21.1, and it's actually going to be split up into two pages here that show different ways that we represent organic molecules. So the first one here is a space-filling model. Carbon atoms are represented with black balls, hydrogen with white balls, and other elements have other colors that represent them. And this is the most sort of realistic picture of what a molecule looks like. Where are its boundaries? What parts are most likely to be touching other parts of the same molecule or parts of other molecules nearby? And so that's a space-filling model. As you can see, molecules are actually pretty round and globular looking, and in some ways space-filling models are kind of hard to really interpret. How many carbons are there in that model? You have to look real close and count really carefully, and so we don't use space-filling models unless we want to talk about the actual sort of surface area and shape of a molecule. You'll often see the next row down ball and stick models. Here the colors represent the same thing. Black is carbon, white is hydrogen. And balls are used to represent the atoms, but instead of having the ball be like the actual size of the atom, we just shrink everything down, and it kind of trims away all of that space so that you can see more clearly what's going on. For example, here it's very obvious that there are 4 carbons. Those are obviously needing to be rendered by a computer or perhaps by a very skillful artist. But we'll move soon into the sorts of representations that you can draw by hand. So here we have structural formulas that include the bond angles. You'll notice that some of the bonds drawn here are solid lines. Those solid lines are bonds that actually lie within the plane of the paper or the board or the screen or whatever. Then you've got bonds that are drawn as dashes or as wedges. So the dashes are bonds that are receding away from your view in three-dimensional space, and the wedges are bonds that are coming out toward you in three-dimensional space. And I wish I had my molecular models kit with me. I don't actually have it, so I can't I don't know, show you a model in 3 dimensions. But hopefully you can look at the ball and stick model there, for example, and they have that ball and stick model in the exact same orientation as the structural formula with bond angles, so you can see what we mean by some of those bonds coming out at you and receding away from you. In fact, having those two illustrations next to each other is better than I could do with a model. I will point out one little thing. It's always been a pet peeve of mine. If I'm going to draw carbon, hydrogen, and hydrogen, you'll notice those angles are actually at about 109.5 degrees, at least if you're drawing it properly. And then you're going to have one hydrogen that's coming out at you, and I'm going to sort of exaggerate how that wedge works, but you know, it tapers, and I think that gives it a sense of three-dimensionality. And then I'm about the only person in the world that does this, but I think I'm right, so I will continue stubbornly to do it. When I draw wedges, when I draw dashes as opposed to the wedges, I like to put the wide end on the carbon and the narrow end out on the atom that's connected to the carbon. I think that that makes more sense three-dimensionally to show that that bond is receding into the distance. I'm like literally the only person on Earth that does that, and I'm probably wrong, but I'm also fantastically stubborn, and so I'm sticking with my ways. As you can see in the textbook and in every textbook I've ever seen, they always have the pointy end on the carbon. So, and then you can get more simple representations. So the structural formula is really just a Lewis dot structure. Now everything is drawn at rigid right angles, 90-degree angles, and that's not what the molecule really looks like. But it does convey what atoms are bonded to what other atoms, just like any Lewis structure would. And so it's still useful. The condensed structural formula just looks for ways to make the formula shorter. Like, for example, here in this butane, in this molecule here, C4H10, you can see that there's a CH2 and then another CH2. Well, let's just group them together and put parentheses around CH2 and then put a little 2, and that'll make it a little bit better. Now, it's not a dramatic improvement in this case, but for very long molecules, I think it can really reduce the size of your structural formula and can be really useful for simply representing really large molecules. And then lastly, we've got the molecular formula, which is simply C4H10. How many carbons are there? How many hydrogens are there? And this is what we've used up until now. The molecular formula has been good enough. The real problem is we don't know how those carbons are arranged, which carbons bond to which carbons, where are the hydrogens bonded. There aren't a lot of options for a small molecule like C4H10, but you know, the larger a molecule gets, the more diverse ways that you can arrange those atoms together, and so the molecular formula becomes sort of like less and less useful for larger and larger molecules. So you can turn this off for a sec. All right, so the first class of organic molecules that we're going to talk about are the alkanes. So alkanes are hydrocarbons. That means they have only carbon and hydrogen, and they have all single bonds. Now, however they're arranged, they're always going to have the same ratio of carbons to hydrogens. So you'll have CN, H, 2N plus 2. So every carbon you have, you'll have 2 times as many hydrogens plus 2 extra hydrogens at the end. And that's how you can recognize an alkane. If I give you a formula like C20H42, of course, we can arrange those all sorts of different ways, but just at a glance, you can see that ratio. C20H42 fits the formula for an alkane, so you know that it is an alkane. You know that there are all single bonds. And in an alkane with all single bonds, you have as many hydrogens as you can possibly put in that compound. And so sometimes these are called saturated compounds. They're not saturated with water, they're saturated with hydrogens. You can't have any more hydrogens than that. And we'll contrast saturated compounds with unsaturated compounds in a few minutes here. Alkane carbons are always, so the carbons are always sp3 hybridized, and that means that they're going to have angles of 109.5 degrees and that's a long word, tetrahedral molecular geometry around all the carbons in alkanes. So alkanes are named according to their own special rules. Let me advance the slideshow a bit here. Oops. There we are. Okay, so first I'm going to put up my PDF notes. Okay. So the first rule here is that the name is going to be based on the longest continuous chain of carbons. And I want to point out, especially if you're looking at structural formulas or Lewis structures, that may not always be obvious for you to see. So if I have carbon, 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 carbon. Okay, and I'll leave off the hydrogens for now because they don't really matter. Looking at this, it's tempting to say, well, this is an organic compound that's based on a chain of 5 carbons that has something branching out off of it. And the way I've drawn it, you'd be forgiven for making that assumption. But when you look closely, you can notice that the longest possible chain of carbons is not 5 long, but it's 1, 2, 3, 4, 5, 6 long. And so what this really is an organic molecule that is based on a chain of 6 carbons long with something branching off of it. Now, if you're drawing organic compounds, then it's probably good form for you to write the longest carbon chain on the top, right? But if you're a teacher that's trying to illustrate a point and maybe being impish and writing it badly on purpose, then you might draw it like this. So the longest chain in this case would be 6 carbons long. So once you have that number, you can come up with a name that's based on these kind of unusual prefixes. You can see this isn't the complete name for the compound. This is what we'll call the parent name. And we'll modify the parent name according to what other elements might be a part of this organic compound. But the parent names here for 1 carbon is methane, for 2 carbons is ethane, for 3 carbons is propane, 4 carbons is butane. You've probably heard at least some of these names before, but they don't follow like mono, di, tri, tetra, penta prefixes that we're familiar with. I honestly don't know where ethane and propane and butane come from. They may have been named before people had any notion of how many carbons make them up, because these are substances that have probably been known for a very long time. I don't know for sure. Once you get to pentane and hexane and heptane and octane and nonane and decane, well, then they start to make a lot more sense. Octane has 8 carbons in it. These are the parent names, and they're based on the longest carbon chain. Okay, let's get my notes back up. Oops, and I can't scroll them until I do this. All right, and then you're going to have branches, like here we've got a branch, which is just where a carbon or some other non-hydrogen element, it could be an oxygen, it could be a chlorine or a fluorine. Anyway, when some other interesting thing branches off of the main carbon chain. For branches that are composed of carbon and hydrogen themselves, sorry, I gotta navigate to the right slide here, then you can name them according to this table here. CH4, a branch of just CH3 would be a methyl group. Again, it's based on that meth prefix that the parent name of methane is. 2 carbons would be ethyl, 3 carbons would be propyl, 4 is butyl, and then we've got kind of some unusual ones. Isopropyl is 3 carbons, but they are linked through the middle carbon instead of the end. Isobutyl is 4 carbons, but again linked through, it has like a branch coming off. Sec-butyl is linked through the second one. Tert-butyl has 1 carbon that then further branches out into 3 other carbons. Tert-butyl. I wouldn't worry so much about memorizing these names here. Whoops, there's my finger. I wouldn't worry so much about memorizing these names. You'll encounter them later. You'll certainly learn them eventually, but for this class, for the exams that I'm going to give you, I'll kind of stick with branch names that are methyl, ethyl, propyl, butyl, pentyl, like that. Okay, let's get the notes back up again. Now the position of the branch is counted from the end such that the branch point has the lowest possible number. And so if we're looking at this molecule here, why don't I go ahead and fill in my hydrogens? It's kind of a pain, but at some point it's going to become essential that my example here be a little bit more of an accurate, true problem. Okay. And you may be wondering, how did I know where to put the hydrogens? Every carbon needs to have 4 bonds, and so I just fill up the empty spots with hydrogens. All right, now it looks actually a lot more cluttered, but it's the same molecule. And we identified our longest carbon chain here as being 6 long. There's our longest carbon chain, and so our parent name is going to be hexane. And then we identified a branch here. I'll use a square maybe. So there is a branch. The branch is 2 carbons long, and so this is going to be ethyl heptane, because it's a heptane with an ethyl group attached to it. But I could have attached this ethyl group various different places, and so we need to identify where it attaches to that main carbon chain. And so we're going to see which end is it closer to. So it's only 2 carbons away from this end, 3 carbons away from that end. So we will start numbering our carbons from here. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So which carbon does the ethyl group attach to? That would be carbon 3. So this is ultimately going to be 3-ethylhexane. So you write the attachment point, then a dash, and then the branch name and then the parent name with no space or dash or anything here. 3-ethylhexane. We've just named this molecule. So the position of the branch is counted from the end such that the first branch point has the lowest possible number. That's why we started counting from here instead of from there. For multiple substituents, use prefixes di, tri, tetra, etc. So why don't we write a new compound here? These are a bit tedious. Okay, so if we look at this, here we've got our longest chain is 4 carbons long. And you know, I could have bent it down or upward and we would have had the same number of carbons. I just kind of want to point that out. And here we have one branch. Here we have another branch. So what do we call this? 4 carbons long. It is a butane. And then what sort of branches do we have? Well, they're both methyl groups, so it's a methyl butane. But the fact that there are 2 of them, I'm going to use that di prefix to say I have 2 methyl groups. Dimethyl butane. Now, where are those methyl groups located? This is carbon 1, carbon 2, carbon 3, and carbon 4. They're both located on the second carbon, so I'll put the attachment point of the first methyl, comma, the attachment point of the second methyl, dash. 2,2-dimethyl butane. If this had been over there instead, it would have been 2,3-dimethyl butane. So you will list each attachment point even if they're both the same, and you'll separate with commas. If we had 3 methyl groups, like maybe one here, here, and here, then it would be 2,3-trimethyl butane. You can see these can get a bit complicated, but they follow a rigorous formula, and it should be unambiguous, really, what name applies to what structure or how to get a structure from a name, as long as you follow the rules. Okay, the next step, oh yeah, there are a couple of weird steps here. So step 5 is really just how to do step 1 properly. So let's suppose that I'll erase the name. Okay. Let's suppose that I gave you this structure and you said, oh, the longest carbon chain is 3 carbons long, and so this is, I'll have to redo my numbers here. 1, 2, 3, and you want to say, oh, this is 1,1-dimethyl propane. Well, step 5 says an apparent branch on the first or final carbon is not actually a branch at all, but a continuation of the main longest chain. And so what we really would want to do is say, well, this isn't a propane, this is a butane, and Professor Rowley just drew it badly. It's a butane with only 1 methyl branch on it on the second carbon. So step 5, I wouldn't have put it as an individual step, but your textbook did. It's just a bit of a warning about how to do step 1 properly. Step 6 says that numbers may be omitted when a branch position is unambiguous. So, for example, you could just call this methyl butane. There's nowhere else that you could put the carbon, the methyl group, other than the second carbon. So let's explore some different possibilities. This is methyl butane, right? Methyl butane. And we could say it is 2-methylbutane. Now, what if we moved this carbon to be on the first? So the methyl group is on the first carbon. Well, then it's not butane anymore at all, it's pentane. What if we move the carbon to be on the fourth? Then it's also no longer a butane at all, that would just be a pentane. What if we moved it to be on the third carbon? Well, then we'd just start counting from the other end and it would still be the second carbon. There is no place we can put that carbon where where it's still going to be a methylbutane, any place we put this carbon where it is still a methylbutane, it will always be in the second position. The same sort of thing with methylpropane. Anyway, technically you can omit the number, but I actually recommend that you just put the number there anyway. Otherwise, the person that's reading it, methylbutane, is going to scratch their head and they're going to think through all the different iterations. They're going to say, what did they really mean? I feel like it should be on the second one, and they'll have to run through all the iterations and make sure that that's really what you meant. So I think it's clear communication to just put the number anyway, which means for number 6, I would say just include the numbers for step 6. Okay, step 7. Now I'm going to have to draw quite a molecule here. Sorry. Alright, so I'll do, I think I can make it work with 6. 3, 4, 5, 6. And then I'll put 1 carbon here, and I'll put 2 carbons there. Okay, and you know what? I could fill these out with hydrogens, but I think it would just be 5 minutes of clicky chalk noises and it would make the board look like a mess. So why don't we just recognize that there ought to be a whole lot of hydrogens on here, but as far as naming the compound, all we care about is the carbon backbone and the branches. We don't care about the hydrogens themselves. So looking at this, this is going to be a hexane. And there are kind of 2 different ways that we could count this. We could have the hexane right across the 6 carbons in a row here. Or we could have 4 carbons and then come around here. So if we do it on the top, then we're going to have 2 branches. One of them is the closest, is only 1 removed from an end. The other is 2 positions removed from an end. If we do it this way, then we've got this funny isopropyl branch, and it is 2 positions away from the end. Anyway, we are going to want to define our main backbone in such a way that the first branch appears as close as possible to the end. And we're going to say this is carbon 1, 2, 3, 4, 5, 6, so that our first branch is closest to the first carbon. So we've got 1 branch here. This is a methyl. And then we've got 1 branch here, and this is an ethyl. And we can do even a little bit better. This is a 2-methyl, and this is a 3-ethyl, because the methyl is, oh shoot, I'm just going to rewrite that and that, sorry. I do want this to look a little nice. So this is a 2-methyl and 3-ethyl. And the whole thing is a hexane. So we can start to write this name, but is it going to be 2-methyl 3-ethyl hexane, or is it going to be 3-ethyl 2-methyl hexane? This is where rule 7 comes in. Different substituents are listed in alphabetical order, and that excludes prefixes if we'd had like a dimethyl or a triethyl. You ignore the prefix. What we're looking at is alphabetical order for that E and that M. And so E comes before M. That means it's going to be 3-ethyl where are we? 2-methyl hexane. How about that? 3-ethyl 2-methyl hexane is the name of that compound. All right. Now those are all the rules according to your textbook. They have a little paragraph that addresses halogens, and I decided to make it an 8th rule, and that is that instead of a carbon branch, you can have a substituent that is a halogen, and they are called fluorochlorobromo. So let's do let's look at this compound, and we'll fill in the hydrogens because that's not too bad. Okay, so that's our compound. It is a propane. We'll start counting from this end. So this is a 1-fluoro group. This would be a 2-bromo group, and B comes before F. And so what is this? 2-bromo, 1-fluoro propane. 2-bromo, 1-fluoropropane. So if you had a chlorine on there, it'd be chloro. If you had an iodine, it would be iodo. And that's where we're going to end with the other elements. There are plenty of organic compounds that contain oxygen, nitrogen, and sulfur. They are not counted as alkanes, and they have their own naming conventions. We'll actually explore those a little bit tomorrow. So these are the only ones that you really need to worry about. So let's so I'm going to draw this compound. So these are a couple practice problems. Okay, is that right? No, it isn't. I apologize. There we are. Okay. So again, I'm going to skip filling in all the hydrogens. They would be all around here. So looking at this compound, I've intentionally drawn it in like a confusing way. So what is our longest chain? It's not the 5 across the top. The longest chain is going to look like this. And I could have jumped to the left or to the right, that doesn't really matter. But that makes this a hexane. And then we've got 2 branches, here and here. This one is the closest branch to either of the ends, so we'll define this as carbon 1, 2, 3, 4, 5, 6. That makes this a 2-methyl, and this is a 4-ethyl, and you can see on my PDF here what we have is 4-ethyl 2-methyl hexane. The ethyl is written first because E comes before M in the alphabet. Okay, so that's a structure going to a name. Can we go from a name to a structure? So if I have 2, 2 dichloro 4, 5 methyl hexane, that's quite a name. Let's break down how we can draw the structure. It's a hexane first of all, so I'm just going to draw 6 carbons. 1, 2, 3, 4, 5, 6 carbons. Okay, and then let's look at what substituents or branches make up the rest of this molecule. Dichloro means I'm going to put 2 chlorines. Where am I going to put them? Both on the second carbon, Cl, Cl. And then I've got 2 methyl groups, one of them on the 4th, and one of them on the 5th. So there are my 2 methyl groups, and I'll just fill in my hydrogens now. Okay, so those are the, that is the correct structural formula or Lewis structure for 2,2-dichloro-4,5 methylhexane. Okay, let me find the right spot for the slideshow. Sorry, I forgot how many slides I need to skip here. Oops, there we are. Okay, so all alkanes are going to undergo similar reactions. You know, you could probably make a catalog of 10,000 different alkanes, and luckily you don't need to then have another catalog of 10 million different reactions that those alkanes can undergo. You can, they're all going to react in a similar way. I actually like my notes better than the slideshow, so I'm just going to scroll down on my notes. Okay. So the first type of reaction, we've seen plenty of this. You can see an example of it down at the bottom of the screen. So complete combustion, when any alkane is... oops, I put... actually, my notes, I messed up a little bit, but we can put any alkane in the presence of oxygen and heat it up, and it's going to produce carbon dioxide and water. That excess that you see, that should have been on the oxygen. So if you have an excess of oxygen, then you will get complete combustion, producing carbon dioxide and water. Incomplete combustion happens when you don't have a high enough concentration of oxygen. You'll notice that the products here are carbon monoxide and water. So if you have a lower concentration of oxygen, then you'll be producing some carbon monoxide instead of carbon dioxide. And then halogenation reactions. If you have an alkane and you put it in the presence of bromine, fluorine, chlorine, or iodine, as long as you have a high enough temperature to drive this reaction, then one of the hydrogens will get replaced by that halogen, and it will produce the hydrobromic acid in this case, or hydrochloric or hydrofluoric or hydroiodic acid if you use one of the other halogens. Now if you have an excessive amount of the halogen, then it will continue replacing hydrogens. Ultimately, you could get something like carbon tetrabromide, CBr4, and 4 hydrobromic acids. So that is it for the saturated hydrocarbons or the alkanes.